by and large, the business data, and that too hitherto, has been structured. Most of the business data today resides in relational databases, and that is what software engineers are accustomed to handle. And most of the data mining that has been studied is also done keeping in mind that the storage is in a somewhat structured relational or equivalent. But the recent trend is in the growth of data which is of different structures. So when we say unstructured data, this is not purely unstructured in the sense we will look at now graph mining. The graph cannot be considered as an unstructured data, but the structure is not as simple as the kind of structures that we deal with typically in the business, that is relational structures or tables. So let's look at the how we do the graph mining, considering that it has got a very complex kind of structures. The fact is the graphs are very widely prevalent. So there are so many things around us, they are best represented using the graphs. So be it the network of roads, be it the communication network, or if you look at the chemical compounds, or the program flow or structure. And so there are, and then the web itself is representing a network, so which can be represented as in a way, graphical form. So we will be looking at what kind of mining that we can do, considering that we have a large number of data, which is graph. Essentially, we have possibly, if you look at each city's, let's say, the power grid, or each community's water grid. So possibly you're going to get millions or many millions of the such graphs for just this information. So we want to look at how to find the patterns or to gain insight into such data. So when we talk about graph, it is a more general entity. So we can have more specific, such as trees. Tree is a form of a graph, such that it starts with a root and ends with a leaf, and there is no cycle within that. So there is there is nothing like a circuit within a tree. But graph is a general structure where you connect nodes with edges with no restrictions. And even among the graphs, there can be a wide diversity. They can be directed and undirected, or they can be graphs with diverse forms of edges where you need to give label to the edges and even the nodes. And and then the relationships can have the weightages. There can be geometrical association as well. So particularly if it is related to the geographical elements that you're trying to connect. So in that sense, there is a wide diversity of graphs that we deal with. And hence finding the structures, patterns and similarity is all challenging compared to the regular numeric or text kind of data that we deal with in business. So when we are looking at graph mining, we are going to look mainly at how to find the subgraphs which are frequent within the graph. Suppose you got the million graphs that are representing, let's say, the road networks in all the communities or the towns. Then you possibly want to see that there are some frequent substructures within all the graphs. And they can also be, sometimes we want to do a constrained substructure. So we want to know only existence of only a specific structure, or we want to find out a substructure which is of a specific nature. And we may also use this knowledge to work with graph index, or essentially we need the indexing on the graphs so that the mining tasks are facilitated. And accordingly, we create the types of index that facilitates the task that we are doing. And we may also want to do the similarity. It's essentially that helps us doing the classification, clustering, etc. So like the frequent pattern mining in normal business data or the relational data, here also when we are talking about the frequent subgraphs within a database of graphs, we will look at a similar thing. That is, we will look at a subgraph which is frequently occurring among the graphs that we are analyzing, and we will also look for minimum support threshold to separate out the ones which are frequent and which are not. And this has kind of applications in several areas. And now let's look at a priori based algorithm for doing the frequent substructures within the graph database. So here what we do is that we start with a graph data set, and we also need to determine upfront the minimum support required. And then what we do is that we start with initially, like in the a priori algorithm that you may remember for frequent item set mining. So we find out all 1 items which are frequent, which have got the minimum support or higher. So we are going to initially create a set which contains all the frequent single element sets, subgraphs within the graph data set. Then we are going to call this in an iterative way, this routine, the a priori graph. And what we are passing is that we are passing the data set, all the graph data set, and then we are passing the minimum support, and we are starting with the initial 1 item sets. And what we do is that, and in general, the way it starts with is that whenever we have got at the kth iteration where we have got the same first 2 parameters are same with, this is the k frequent item set. So those are the frequent subgraphs which have got the k elements within it. So we start with our approach is, in this case also, we always find out sk plus 1 using sk, so that we know that the sk is representing the frequent subgraphs. And so we are looking at only the graphs where the sk is subgraph. So we are expanding the sk to create the new frequent subgraphs. So to start with, sk plus 1 is 5, that is null. And then for we looking at sk and finding out each frequent gi, gj, so these are the 2 subgraphs which are frequent. Then based on these 2, we are creating a new graph g, which is a combination of gi and gj. If in case of a frequent item set mining, suppose you have got a, b, c is 1 frequent item set, and then b, c, d is another frequent 3 item set, and then the candidate 4 item set will be a, b, c, d, which is a union of these 2. So similarly, we are doing the gi and gj, we know are the frequent, and we are trying to create k plus 1 item element subgraph. And what we do is that we merge gi and gj and create a new subgraph g which has got k plus 1 elements, and we check if it is frequent in D. If it is frequent and if it is not already present in sk plus 1, then we are going to insert it into sk plus 1. And after completing this loop, we check that sk plus 1 whether it has got any new or any subgraphs at this level. If it is null, then we are, if it is only not null, we are going to proceed. So for example, at 5 element subgraphs, we see it is null, then there is no point in trying for 6 element subgraphs. So if it is null, non-null, so then we are going for the next level. Otherwise, we are closing the algorithm. So the way it works is that we are starting with the k-edge subgraphs, and then we are joining them. So for example, g and g prime are joined to create g1. Similarly, we are creating k plus 1 edge subgraphs from this, and then based on that, we are finding out whether these the newly formed subgraphs are frequent or not. But the challenge here is that when you have got 2 subgraphs, both of them are of the k elements. If we want to create k plus 1 elements, there can be multiple new subgraphs that will come up. So it is not going to be few. It can be multiple. For a larger subgraphs, it can be many. So now let's look at an example. Suppose we have got two subgraphs of this kind, and then we have decided that we create a new graph with adding one more node. So here we have got this is common, and then what we decided is that we want to add one of the nodes. So when we add one node, then we can get this, and we can also get this type of subgraph with the same just addition of one node, because we have not considered the edges. But if we consider even the edges, so in this case, this is the approach proposed by one authors, and another set of authors proposed in another algorithm where you create new graphs by adding a edge. So in this case, what happens is that the edge can be added at many ways. So the point to be noted is that the graph can exist in many isomorphic forms. So we can say this is X. Okay, so we can also have another graph Y. Though it looks different from X, we can make out that this is an isomorphic graph. So it is a graph that is obtained by just rotating it. So what happens is that, so when you try to combine these two graphs by adding a one more edge, you get so many potential new graphs that are possible. So for this region, when we are trying to create a higher order k plus 1 element subgraphs, we have a large pool of candidates. So one of the challenges here is to how to prune those candidates. So the another approach we can take is that instead of trying to create so many candidates, we can go by a pattern growth approach. So what we do is that we have got k edges, and then we consider k plus 1 edge instead of joining by expanding the k edge, and from there k plus 1 we can get k plus 2. But because of the isomorphic nature of these graphs, which can be drawn in several formats, but they mean the same thing. So what happens is that we may end up with a numerous duplicate graphs, because once we remove all those graphs which are same structure represented in a different format, because as we know, the graph one way in which we can represent is the linked list. But the point is that whenever you are representing it, the start node may be different and then the end node may be different, but then it may still represent the same graph by different sequence or by starting at a different point. So for that reason, we end up, it is very difficult to find out the duplicates. And because of that, we get a large data of large patterns, number of patterns, but many of them are redundant. And as you can see, this is a challenge, because it's also, when we are looking at the number of subgraphs, then it's a challenge. For example, we have got an n-edged frequent graph. Then to consider what are the total number of frequent subgraphs that are available for this graph data set, we can see that from n-edged frequent graphs, we can create 2 to the power of n subgraphs. So what that means is that we have to deal with a very large number of candidates whenever we are doing this graph mining. So as an example, here when we are looking at 422 chemical compounds which are related to a particular drug, a particular disease and disease treatment, then what happens is that when we are trying to look for the subgraph patterns which have got a simple 5% minimum support, we are ending up with 1 million frequent graph patterns. So if we want to do further analysis for any drawing further insights, it's going to be a huge challenge because of the large number of these subgraphs. So one way we can handle this is with the help of the closed frequent graphs. So as we have done it in the earlier frequent item mining, so a closed frequent graph is such that there are no supergraph that carries the same support as G. So in that case, we call that as closed. So then what it means is that anytime you have a subgraph which has got the same support as its supergraph, then there is no point in carrying forward the subgraphs for the purpose of further analysis or further processing. So thereby we are going to prune some of the candidates or some of the subgraphs that we need to work with. And when we are looking at the graph clustering, that is, we are trying to create the graphs which are similar. Essentially, we have got, let's say, 1 million graph database. We want to cluster, so create the small number of clusters that represent the similar graphs. So here we need a similarity measure whereby we can see that the two graphs or many graphs are similar. So there are approaches in which we can take. One is that we can use the features of the graph to represent the compare two graphs and look at the similarity between the features, and the features can be represented as vectors. Again, the features can be of diverse types, because considering that the nodes can be in a graph can be diverse, and then the links can be diverse. So for example, when we are connecting two towns and with a road network, we can talk in terms of connecting the two towns with a 2-lane road, 4-lane road, 6-lane road. So essentially we can have a diverse forms of edges which connect. Similarly, each node can also be represented with a different types, because it's not necessary that in a graph every node has to be of the identical kind. So for that reason, what happens is that when we are picking up the features, we can pick up the features of several kinds. So it can be the counts of various things, or it can be even one feature can be the subgraph itself. We are looking at whether it contains what are all the frequent subgraphs within this graph. And we can form a vector that shows all the frequent subgraphs, and we can see whether there is any other graph which has also got a similar set of frequent subgraphs. So thereby the feature-based similarity is essentially converted it into vector analysis. Or otherwise we can do a structure-based similarity where we can work with a maximal common subgraph that exists between the graphs, and then we are going to look at the insertion, deletion, relabel, etc. to measure the distance between the two subgraphs. So thereby we can see that these two subgraphs are same except for one relabel of one of the edges. So thereby we are going to look at the distance between or the similarity, and thereby we can create the cluster. As we know, in the cluster we need to make sure that in each cluster the elements within that have a minimum distance, and then there is a lot of distance between the elements across two clusters. And again, when we are looking at the classification, when we may do with based on the neighborhood, so that is we can say that if it has got a particular type of a vertex with a particular type of neighborhood, then we are saying that we are going to classify it as in one of the classes that we can decide upfront. So what are all the classes that we look for? Or we may look it based on not single vertex but a subgraph pattern. And again, the subgraph pattern may come from a domain knowledge. So that is, we know that, for example, a communication network, a network engineer can easily tell some specific sub networks that always exist within a communication network. Or we can determine the subgraph patterns based on the data mining. When we are doing the data mining, we come across let's say we have done the frequent subgraph mining, and then from those subgraphs we can determine how to classify a particular graph. And when we are talking about subgraph patterns from a domain knowledge, for example, when we are talking about either a molecular descriptions that can come from the chemist or from a data mining, we can represent these subgraphs in the form of a feature vectors. And then when we are looking at, and we can say that each vector is associated with a class label, and thereby we will be able to create a classification. And we are interested in whenever we are trying to analyze the subgraphs or the graphs for the similarities. One helpful thing will be the ability to search the graphs. And for that, if we can create some form of index and some mechanism whereby we can check the existence of a graph, then that can facilitate the graph mining tasks. And now we are moving into a topic which is related to the graphs, but of specific kind, because when we are looking at a web or social networks, we know that there are a lot of connections or the links that exist between the elements within the or the objects within the network. So in a way, it represents a graph mining problem. But here, some of the nomenclature and some of the techniques that are used and some of the parameters of importance are different. So here you may have the nodes which are representing the objects of many different kinds, or for example, a member of a social network can be an object. Then in that case, the object will have several attributes, and object itself may have labels or classes. And again, similarly, the edges can be of many types, and the edges also can have the many attributes, or the edges can also have the direction. And it's also not necessary that they have to be binary, so they can be of several levels. So it is not just exists or not exists. So if we look at a social network model, so we may get individuals in a tight social group that is referred to popularly as a clique, or individuals who are connected to many groups, but they don't belong to a single group, but they're connected to many groups. We may consider them as a hubs. And so it's essentially a leader-like people who can bridge with many groups. And then there may be individuals who are outliers, who are residing at the edge and are not connected or linked to any group. So we may get in a social network model all types of people. For example, if you look at this is representing a clique. And here you see a hub or a kind of a leader. So possible that this is a group of people who are representing, let's say, artists. And here we have another group, which is a clique, which is representing, let's say, a software engineer. So possibly somebody who is bridging them is some kind of a leader, or you may say so. In one way you may represent. And then there may be someone who is not connected to many members of a group and has a minimal connectivity. So you can call such members as outliers. And we can represent the neighborhood using a neighborhood function for each node. And then we can also measure the structural similarity by essentially doing something of a cosine similarity between the vectors. So when we do this kind of structural similarity for members of clique, we are going to get for a large number of members of the clique, all of them are going to get somewhat a similar structure. But it is going to be very different for people who are of the category of hubs and outliers. And when we have this web and social networks, sometimes we want to do a link mining, which a link is representing a relationship, which can either be a homogeneous or heterogeneous. So when we are talking about a homogeneous, for example, in a social network of friends, the connections among all the friends, we may treat them as homogeneous. So here we are talking about object type and link type, everything is homogeneous. But many times we may also come across the heterogeneous. For example, here we are talking about, let's say, a patient and a doctor. So a doctor may be connected to 100 patients whom he is monitoring or treating. So in this case, but the two elements, two objects which we are talking about, patient and doctor, they're not similar. And the linkages from doctor to patient is not same as the linkage from patient to doctor. So similarly, you can have an object of the type disease, contacts, treatments, etc. And you're going to connect all of them. But each one of them is representing a different type of object. And similarly, for a bibliographic network, you may get the authors, publications, etc. And we may create, based on the link, we can create the object ranking So what happens is that we can use the links to determine or to assess the objects within a graph. So there what we do is that here some of the examples are the page ranking and hits. These are going to help us with the link based ranking. So for example, if some object is being reached through some link, then we know that it is representing a particular type. So essentially we classify or categorize all such objects, and then we are going to get insight. So we may be able to do here the based on the centrality, and then we can also use it over a period of time, that is with respect to in a dynamic approach. So that is how is it changing over a period of time. And one popular algorithm is the page ranking algorithm proposed by Brin and Page. And here the approach is that we look at the links and treat the links as a citations in literature. For example, whenever there is a research paper, it refers to many other references which have been referred for creating this new research paper. So similarly, the links can be treated the same way. So if many other pages are connecting to this particular page X, then we say that this X is popular, or we can give X, the page X, high page ranking. So in a way, the page ranking can be considered as a citation counting, but this can also be indirectly increased. For example, if you are connected from one of the influential magazines, then we can increase the links weightage, and thereby we can increase the page ranking. So thereby we are going to get the comparison of the various members of the web, that is various pages in the web. So now we will look at some of the challenges when we are working with the graph mining. So as we have noticed, the candidates and then the patterns are very large. So the computational cost is going to be very high, as it is finding the similarity or finding the isomorphic graphs is not an easy problem. And the graphs can be sometimes sophisticated. They can involve the weights. So that is, each node can have some weight and each edge can have some weight. And then there can be cycles. So because of that, the computation becomes even further complicated. And we can also consider that graph in a way as a high dimensional structure. So that is to say, if we have got a graph which has got 100 nodes, then we can treat this essentially as 100 dimensional elements that are there, and thereby the linkages among them and then the meaning of each one of these nodes is going to represent the characterization or the clustering for the graph. So what we can see is that this is becoming really a high dimensional problem. And added to that, there can be because of the large number of nodes does not mean that the large number of connectivity. And particularly when we have got a large for example, when we are talking about, let's say, a road network, let's say there may be a 100,000 towns in the country, but then each town is not connected directly by road to every other town. So it is possible that it is only connected to 3 or 4 other towns by road, and if you want to go to a distant town, you have to pass through many other towns. So what that means is that we have got a graph with 1 lakh nodes, but the connectivity is very sparse. So when we are looking at out of those 1 lakh towns, you are connected to only 5 towns. So you are dealing with really, when you try to make it a sparse, the matrix representation to represent the connectivity between the nodes, then you are going to get a large matrix with high sparsity. So we'll have to use the sparse metric techniques to handle this kind of large matrix problems.